Hello, everyone, and welcome to our final lecture in Unit 1. We will be all reviewed and ready to start true AP Chemistry content. Who's excited? Okay, so our last thing is stoichiometry, and it's usually a word that everybody remembers from chemistry. They're like, oh yeah, that's stoichiometry stuff. What was that? Something with the mole. All right, so we're going to review it really quick because you're going to remember it. All right, so stoichiometry is just a calculation of relative quantities of reactants and products in a chemical reaction. So it's just mole conversions. We're just adding a new conversion factor. And that new conversion factor is going to be the mole ratio. The mole ratio is simply the ratio between moles of two substances in a balanced chemical equation. Now, if our equation is not balanced, our equation is incorrect. And if our equation is incorrect, then our mole ratios are incorrect. So we always have to start with a balanced chemical equation. Okay? So now we can use this ratio as a conversion factor. So this equation down here of the creation of water, the synthesis of water, I know that 2 moles of hydrogen. So before we were saying 2 molecules, which is true, but we can also say it's the whole 2 moles. These are also molar coefficients. 2 moles of hydrogen gas react with 1 mole of oxygen gas to make 2 moles of water. So whereas before we were only using a mole ratio, a molar conversion for one substance, maybe how many grams of hydrogen are in 1 mole of hydrogen, or how many liters of hydrogen would be in how many grams of hydrogen. Now we can hop from one substance to another. 2 moles of hydrogen equals 1 mole of oxygen. That's just simply, 2 moles of hydrogen equals 1 mole of oxygen. So all this is another conversion factor. So for example, one way of producing oxygen gas is the decomposition of potassium chlorate into potassium chloride and oxygen gas. How many moles of each reactant are used? So the first thing that we have to do is we have to write a balanced chemical equation. So potassium chlorate is KClO3. And it says it decomposes into potassium chloride and oxygen gas. Now I've written my reactant and my 2 products, but now I have to see if my equation is balanced. And it's not, because I have 3 oxygens on this side and I only have 2 over here. So I'm going to put a 3 in front of this, which gives me 6. So I'm going to put a 2 in front of this, which gives me 6 oxygens. But now I have 2 potassiums and 2 chlorines, so I'm going to stick a 2 there. Now, these are my coefficients, which are my mole ratios. So what that means is we have 2 moles of potassium chlorate. And then we have 2 moles of potassium chloride are made, and 3 moles of oxygen gas are made. And now any of these can be written as conversion factors. So 2 moles of potassium chloride is equal to 3 moles of oxygen gas. Any of these are now conversion factors. Okay, so now that we know how to use mole ratios, we can set up stoichiometry problems. So copper reacts with silver nitrate. How many grams of silver nitrate are needed to produce 45.5 grams of copper nitrate? Well, first thing we always have to do is start with a balanced chemical equation. So I'm told that copper reacts with silver nitrate. Now, how do I know what my products are going to be? Well, I look at this equation and I see this is a single replacement reaction. So copper is going to kick out the silver to create copper nitrate and solid silver. So now I have to look and see if my whole equation is balanced, and it's not, because I have 2 nitrates in the products. So I'm going to stick a 2 there, and now that gives me 2 silvers, so then I have to put a 2 here to balance that out. Okay, So for this question, I'm starting with 45.5 grams of copper nitrate because it tells me that that's how much I produce. And it wants to know how many grams of silver nitrate. So I'm doing just a conversion. So I'm starting with grams. I'm going to have to go to moles. Now I'm going to have to go then from moles of the first thing to moles of the second thing, back to grams. Well, how do we go from grams to mole? Molar mass. So I'm going to write down my given, which is 45.5 grams of copper nitrate. I'm going to use the molar mass to convert to moles. Then my new conversion factor is this mole ratio, because I know that 1 mole of copper nitrate is equal to 2 moles of silver nitrate. So there's my 1 mole equals 2 moles. Then I continue on with my normal conversion factor of using the molar mass to go from moles to mass. And then I get 82.4 grams of silver nitrate. So what this tells me is I would need 82.4 grams of silver nitrate to produce 45.5 grams of copper nitrate. All right, so let's try this example. If you would like to pause, try it on your own, and then resume the video, you can do that. All right, so this is the same equation that we had a couple slides ago. So the decomposition of potassium chlorate into potassium chloride and oxygen. Okay. So it tells me that a 25.5 gram sample of potassium chlorate is decomposed. How many moles of oxygen are produced? So this time I'm starting with 25.5 grams of potassium chlorate. Now you'll notice I always include the formula as part of my units, because now since I'm switching from one substance to another, it can get a little confusing, and so it helps to keep it organized to put your substance formula in your units. Okay, 25.5 grams. Now I got to go from grams to moles, so I need my molar mass. So I find the molar mass of potassium chlorate, and it is 122.6 grams. So now I would be in moles of potassium chlorate, but this asks me how many moles of oxygen. So now I'm going to look at my mole ratio. 2 moles of potassium chlorate is equal to 3 moles of oxygen gas. And I get that straight from my coefficients. So when I multiply across the top and divide by the bottom, I get 0.312 moles of oxygen gas. Now my next question says, how many grams is that? If it had originally asked me for grams, I could have just kept going, but it did ask me for moles. So now I'm just going to take those moles and go one more step and convert it to grams. So 1 mole of oxygen gas is 32 grams. Don't forget that it's diatomic. So that's why we have to do 2 times oxygen's mass. And when we do that math, we get 9.98 grams of oxygen gas. And finally, it says how many grams of potassium chloride are made. So this time I'm going to potassium chloride. I'm going to start with my same given, 25.5 grams of potassium chlorate. 1 mole of potassium chlorate is 122.6 grams. Now this time I'm converting to potassium chloride. So 2 moles of potassium chlorate is equal to 2 moles of potassium chloride. And then it asked me for grams of potassium chloride. So 1 mole of potassium chloride is equal to 74.6 grams. I'm sorry, I ran out of space. So when I multiply across the top and divide by the bottom, I get 15.5 grams of potassium chloride. Okay, So another concept that goes along with stoichiometry is the idea of a limiting reagent. This is the exact same thing as a limiting reactant. I was just taught limiting reagent, and so I'm almost always going to use that term because it's what I'm used to. Limiting reagent, excess reagent, limiting reactant, they mean the exact same thing, so they're interchangeable. So what is this idea of a limiting reactant? So let's think for a second. What if we were building tables? And every table requires 4 legs and 1 surface to make the table. So let's say I have 25 tables and I have 5 surfaces. Which one am I going to run out of first? Essentially, I'm asking which one is my limiting reactant. So I'm going to set this up like a stoichiometric calculation. How do I do that? Well, to determine which one's limiting, I'm going to figure out how many tables could I make from 25 legs and how many tables could I make from 5 surfaces. So 25 legs, 4 legs per table gives me 6.25 tables. 5 surfaces, 1 surface per table will make 5 tables. So I can make 6 1/4 tables with my legs, but I can only make 5 tables with my surfaces. So I absolutely would have to stop making tables when I got to 5 because I would run out of surfaces. So that means surfaces are my limiting reagents. Chemical reactions work the exact same way. There is always going to be one reactant, or most of the time there's going to be one reactant that's going to run out. And so that reaction is going to stop when that reactant or that reagent runs out. So the limiting reagent actually limits or determines the amount of product that can be made. So then if one of them is limiting, we can call the other one the excess reagent. And so that's the one that's not used up or is left over. Okay, so how do we know that we need to determine a limiting reagent? Well, if we are given 2 starting amounts, so 2 amounts of reactants, then I know I'm going to have to determine which one's limiting, even if the question doesn't ask me that. Because otherwise, I don't know which one to start with, because I don't know which one's going to run out. Before now, for every stoichiometry problem, we were only given 1 reactant starting amount. And so being given 2 tells me that I have a limiting reactant or limiting reagent problem on my hands. So the way we're going to do this is we are going to convert each reactant starting amount to the product, aluminum chloride. Now let's say I had 2 products. You would just pick one and convert both of them to that same product. All right, so 58.4 grams of aluminum, convert that to moles, moles of aluminum to moles of aluminum chloride, moles to grams, and I get 288.6 grams of aluminum chloride. Now I'm going to do the exact same thing with the amount of chlorine. Now we look at the amount of aluminum chloride that each of them can make. The chlorine can only make 133.3 grams of aluminum chloride. So it's all well and good that 58.4 grams of aluminum could make 288.6 grams of aluminum chloride, but I'm going to run out of chlorine well before I get to that amount. So that means that chlorine is my limiting reagent and aluminum would be my excess reagent. So let's practice this. If 4.95 grams of ethylene are combusted with 3.25 grams of oxygen, what is the limiting reagent? Now, this is going to show you why we went ahead and found how much product each reactant would make, because our work is going to be done. For most problems, they're going to ask us for an actual amount, and so we've already done that work. Okay? So the first thing I have to do is I have to write a balanced chemical equation. And I know combustion reactions are always in oxygen gas, and they always make carbon dioxide and water. So now I have to balance this equation. So I'm going to put a 2 there, and I'm going to put a 2 here, which makes a total of 6 oxygens. So I need a 3 right here. Okay? So now I'm going to convert each of these starting amounts to carbon dioxide. Now, could I convert them to water to figure out my limiting reagent? Yes, I absolutely could convert both of them to water. Now, I have to convert them both to the same thing. But I'm smart, and I see that the next half of my question asks me to determine grams of carbon dioxide. So I don't want to do extra work, so I'm just going to convert each of these to carbon dioxide from the get-go. So 4.95 grams of C2H4. I'm going to convert that to moles. So molar mass, 28 grams in 1 mole. Now I need to convert using the coefficient to carbon dioxide. And then grams of carbon dioxide. You may also ask, could you stop at moles, just to answer the question of which one is the limiting reagent? You absolutely could stop at moles, but again, my next question asked me for grams, so I'm just going to go ahead and do that work. So 4.95 grams of ethylene would make 15.56 grams of carbon dioxide. So now let's see how much 3.25 grams of oxygen would make. Why do I keep writing CO2? Okay. So 32 grams of oxygen is in 1 mole of oxygen. My coefficients tell me that 3 moles of oxygen are equal to 2 moles of CO2. 1 mole of CO2 is equal to 44 grams. So I multiply across the top and divide by the bottom. I get 2.98 grams of CO2. Okay, so my starting amount of ethylene will make 15.56 grams, but my starting amount of oxygen is only going to make 2.98. So that means oxygen is my limiting reagent. And then the second question says how many grams of carbon dioxide are produced. Well, I've already found that math, and I'm going to make 2.98 grams of carbon dioxide. So it's always going to be the lower amount because my limiting reagent is going to run out once I make 2.98 grams. I'm not going to have any oxygen left, so ethylene is my excess reagent. Because labs and anything else are never perfect, chemical reactions usually do not produce the total amount it's expected. So what that means is we call the calculated amount that could be produced the theoretical yield, meaning it's literally theoretical. It's what could be made if everything goes perfectly. This is calculated based on the limiting reagent. It's what we just did. It's what we calculate using, okay, this is how much we have. When it runs out, this is the amount that we could make. That's the theoretical yield. The actual yield is what it sounds like. It is how much is made when the experiment is actually conducted. So this has to be determined experimentally. So theoretical yield is determined through stoichiometry. Actual yield is determined through experiment. Then we can take these two numbers and calculate a percent yield, which shows the efficiency of the reaction. We can take the actual yield, so what we really made in lab, divide it by the theoretical yield, what could have been made, and that will allow us to calculate the percent yield. So, some practice. Calcium carbonate is decomposed into calcium oxide and carbon dioxide. And I give you the equation here. I need to check and make sure it's balanced, and I do, and it is balanced. So I don't need any coefficients. Coefficients here are all 1. What is the theoretical yield of calcium oxide if 24.6 grams of calcium carbonate is used? Now, I am only given one starting amount, 24.6 grams of calcium carbonate. So I don't need to worry about a limiting reagent in this problem because we don't have a second starting amount. So in order to find the theoretical yield of calcium oxide, I'm just going to convert 24.6 grams of calcium carbonate into grams of calcium oxide. So molar mass, 100.1 grams in 1 mole. My coefficients are both 1. And I'm going to calcium oxide. 1 mole of calcium oxide is 56.1 grams. And I multiply across the top and divide by the bottom. I get 13.8 grams of calcium oxide. So that is my theoretical yield of calcium oxide. Now, if I actually do this lab and 13.1 grams is produced, what is my percent yield? So I'm going to take my actual yield and I'm going to divide it by my theoretical yield, what could have been produced if everything had went perfectly. And then, of course, because this is a percentage, I'm going to times it by 100. And I get 94.9%, which is a very high percent yield. All right, here's another example. You can pause if you'd like, and then resume it to see the answers. So aluminum burns in bromine, producing aluminum bromide. In a laboratory, 6 grams of aluminum reacts with excess bromine. So what that tells me is that I have plenty of bromine to use all of this aluminum. 50.3 grams of aluminum bromide are produced. What are the 3 types of yield? Well, 50.3 grams of aluminum bromide is definitely my actual yield, because that's how much I actually made in lab. Now, to figure out my theoretical yield, I have to do the stoichiometry. So I'm going to start with 6 grams of aluminum. Well, in order to know my mole ratio, like always, I've got to start with a balanced chemical equation. So aluminum burns in bromine. Can't forget that bromine is diatomic, and it forms aluminum bromide. So now I have to balance this equation. So I'm going to need a 3 here, 2, and a 2. So now I have a balanced chemical equation. So I'm going to find my theoretical yield of aluminum bromide. So I'm going to go from grams of aluminum to moles of aluminum. And then from moles of aluminum to moles of aluminum bromide. And then moles of aluminum bromide into grams of aluminum bromide. When I multiply across the top and divide by the bottom, I get 59.3 grams of aluminum bromide. Okay, so with stoichiometry, I calculated that I could theoretically produce 59.3 grams. So this is my theoretical yield. Now finally, to calculate my percent yield, I'm going to do my actual yield divided by my theoretical, how much I could have made. Of course, we always times by 100, and I get 84.8%. So then that's my percent yield. All right. Years of experience have proven that the percent yield for the following reaction is 74.3%. If 10 grams of mercury and 9 grams of bromine are reacted, how much mercury to bromide will be produced? So first thing, I have to make sure I have a balanced chemical equation, and I am given one right here. So all my coefficients are 1. So I have 10 grams of mercury, 9 grams of bromine. So I know I have a limiting reagent problem on my hand, because I'm starting with 2 starting amounts and I don't know which one's going to be limiting. So I'm going to convert each of them into mercury bromide to see which one makes the least. So convert to moles. And then moles of mercury bromide. And then grams of mercury bromide. And I'll multiply across the top and divide by the bottom. I get 18.0 grams of mercury bromide. All right. Now I got to do the same thing with my bromine. So 1 mole of bromine is 160 grams. My coefficients are 1 to 1. And that's going to give me 20.25. Now, this question didn't explicitly ask me what's the limiting reagent, but I had to determine what the limiting reagent is to know how much mercury bromide I'm going to make, because one of them is going to run out. Well, I see that the mercury can only produce 18.0 grams, so that means that mercury is my limiting reagent. And so my amount produced is 18 because I can't make 20.25 when I run out of mercury. So my amount is 18 grams. All right, our last little stoichiometric conversion factor comes from the ideal gas law. So the ideal gas law is PV equals nRT. So pressure times volume is equal to the number of moles times the ideal gas constant times temperature. The ideal gas constant is absolutely given to you in your reference table. And for the purposes of this equation, it's 0.0821 liters atmosphere per mole Kelvin. We're going to spend a whole unit later on talking a lot about gases, where we talk way more about ideal versus real gases. But it's assumed for an ideal gas that the particles don't really have a mass and they're not attracted to one another. And that allows them to abide by the ideal gas law. Now, at this point, you do not need to worry about any of that. Like I said, we're going to spend a long time talking about it in a future unit. Right now, you just need to know this equation, but it's given to you on your equation sheet. So the variables and the units within the ideal gas law, so PV equals nRT. So P is pressure, it's in atmospheres. Volume is liters. Amount, the N is number of moles. Temperature is in Kelvin. The unit of R that I just gave you on the previous slide are liters atmospheres per mole Kelvin. So if you are given your temperature in Celsius, you have to convert to Kelvin, or your answer will be wrong. So you have to convert to Kelvin. Okay, so if we remember back when we first reviewed mole conversions, we learned that at STP, and only at STP, 1 mole is equal to 22.4 liters. Well, if you remember, STP is standard temperature and pressure. It's 0 degrees Celsius, not Kelvin, because then we would be at absolute 0. So 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere. So I'm going to show you something. So PV equals nRT, my ideal gas law. So if let's say I want to solve for volume. So volume is equal to moles, ideal gas constant times temperature over pressure. So what is the volume if I have 1 mole and I'm at standard temperature and pressure, so 273 Kelvin and 1 atm. Well, if you do this math in your calculator, you're going to get 22.4 liters. So the 1 mole equal 22.4 liters just comes from the ideal gas law. It's just a lot of experiments and things are taken at STP. And so it's just a kind of easy cheat that, okay, I could do the same math every single time, or I can just memorize that at 1 mole at STP of any gas is 22.4 liters. But let's say that we're not at STP. Then we have to use the ideal gas law to convert, which is going to be more stoichiometry. So again, STP, 1 atmosphere, 273 Kelvin. We know that 22.4 liters are in a mole. But if we are not at STP, we're going to have to do some converting. Okay, so for example, copper reacts with nitric acid to form copper nitrate, water, and nitrogen monoxide gas. Determine the mass of copper that would be required to produce 4 liters of nitrogen monoxide at 1.05 atmospheres and 22 degrees Celsius. Okay, that information right there tells me that I'm not at STP. So I cannot use 1 mole is equal to 22.4 liters. So this question is asking us for the mass of copper, but we don't know anything about the amount of copper. But we do know we have 4 liters of nitrogen monoxide gas, so we have to start there. But first things first, we have to start with a balanced chemical equation. So I have copper reacting with nitric acid. So nitric means that it came from nitrate, so HNO3. Yields copper nitrate plus nitrogen monoxide plus water. And it tells me that in the question. So now I have to go through and I have to balance this equation. If you would like to pause and balance it on your own, you can. Or I'm just going to fill in the coefficients now. All right. So now we have our balanced chemical equation. So we know that we have 4 liters of nitrogen monoxide. And I want to know what's the mass of copper. So I have to go from liters of nitrogen monoxide to moles of nitrogen monoxide to moles of copper to mass of copper. Okay? Now, I'm not at STP, so for this conversion right here, I cannot use 1 mole is equal to 22.4 liters. So instead, I'm going to use the ideal gas law to find the moles. So real quickly, I'm going to rewrite my equation up here. Yield 3 copper nitrates plus 2 nitrogen oxides plus 4 waters. Okay, so I need to find moles of nitrogen monoxide. So my ideal gas law is PV equals nRT. So moles, solving for moles, PV over RT. From my previous slide, I found out that the pressure, or I knew the pressure was 1.05 atmospheres. The temperature was, or excuse me, the volume was 4 liters. Ideal gas constant, 0.0821. And the temperature was, when I convert to Kelvin, 295. Okay. So when I do the math, I get 0.17 moles of nitrogen monoxide. So now my question asked me for grams of copper. Well, now that I know the moles of nitrogen monoxide, I can simply convert that to grams of copper using my mole ratio in stoichiometry.
So 0.17 moles of nitrogen monoxide, I see from my coefficients that 2 moles of nitrogen monoxide is equal to 3 moles of copper. And then 1 mole of copper, I go to the periodic table and see that it is 63.55 grams. I'm going to multiply across the top, I'm going to divide by the bottom, and I get 16.2 grams of copper. So the only difference here is one step of your conversion, if you're not at STP, has to be the ideal gas law. You might have to convert to moles first. With your stoichiometry, then plug into PV equals nRT. Or you might have to do what we just did, plug into PV equals nRT to get moles, and then convert with stoichiometry. All right, this is our last lesson. I know that one was a lot, but we're going to do lots of practice, and I'm going to put a lot more resources up for you, so don't worry. Have a good